Input signal, scaling, input range. As an example, let's take this 6-channel analog input module that has several configurations that must be done after being discovered or added to the project. For each channel, the input range has to be configured depending on the field input analog transducer that will be connected to the module. Each channel of this module can be set up to accept a voltage or current analog input. The setting ranges are -10 to +10 volts DC, 0 to 5 volts DC, 0 to 10 volts DC, or 0 to 20 milliamps current. From the signal that is being monitored point of view, we have to determine the input range of the signal and associate it with low and high signal in the scaling. For instance, if the input range is 0 to +10 volts DC, the low signal can be set to 0 and the high signal to 10, and we can set the engineering units to 0 and the high to 10, thus having the value being read by the module mirror the input signal. If the module reads 0 volts at the input, the tag for the analog channel will read 0. If the input signal is 10 volts, then the tag will read a value of 10. As we know, Allen Bradley's analog modules also have the powerful capability of scaling. This scaling can be done to match the signal being measured and scale accordingly. For instance, if the signal was coming from a pressure transducer that is measuring a range of 0 to 3000 psi, which is proportional to the transducer's output of 0 to 10 volts DC, the module can be set at the low and high engineering units to 0 and 3000 respectively to match the signal. If the module's channel 0 is reading 5 volts, the tag associated with channel 0 will have a value of 1500, which represents the PSI being read at the input from the pressure transducer. Similarly, if we're interfacing a transmitter to channel 1 of this module, and the transmitter provides a 4 to 20 milliamp current proportional to, let's say, a reading of 100 to 600 degrees Celsius, we could configure the module for an input range of 0 to 20 milliamps. The fact that we are interfacing a 4 to 20 milliamp signal into a range of 0 to 20 milliamps does not really matter here, because when we scale the signals, we would get the correct reading value into the tag. So we would set the low signal to 4 milliamps and the high signal to 20, and the low engineering to 100 and high engineering units to 600, corresponding to the 100 to 600 degrees range. If the module is reading 13.6 milliamps, the temperature reading will be 400 degrees. If we're troubleshooting an analog input and the transmitter has been changed from 4 to 20 milliamp to 0 to 20 milliamps, which match the same 100 to 600 degrees Celsius, we would need to change the low signal scaling from 4 to 0 to match the transmitter. Now, a reading of 0 milliamps will represent 100 degrees. Filters, sensor offset, RTS. When we're troubleshooting, we really don't deal much with filters. The notch and digital filters, once they have been set by the programmer, they pretty much stay the same. However, it is good to know what they do and what they're for. The digital filter is used to smooth the input signal transition from one value to another, while the notch filter attenuates the frequency selected, and for us would be 60 Hz. The notch filter also reduces harmonics in the input signal to remove input signal noise. The real-time sample, or RTS, is a setting entered in milliseconds, which determines how often the module goes out and reads the input signal, or in other words, goes out and samples the input signal value to send to the controller when the requested packet interval, or RPI, expires. The sensor offset deals with the need to add off